Hi everyone, welcome back to MATA35. This is we're going to be talking about functions of several variables. So last week we talked about linear algebra. This week we're going to be talking about some multivariable calculus, including partial differential equations, multiple integration, and of course, to get it all started, functions of several variables. First, I want to mention a couple things about the quiz that will be happening next week. So let's switch over to the class website. So if you'll notice, I have a practice quiz up for the practice quiz 2. It will cover basically basic linear algebra operations. So matrix operations, systems of linear equations, Leslie matrices, matrix inverses and determinants, eigendecomposition, and complicated Leslie matrices. Now, this will be a little bit, this practice quiz is much longer than your actual quiz will be. So I have a couple notes here, like for the actual prac quiz, there will only be 2 of these sorts of problems instead of 4, things like that, or like only 1 large system of equations instead of 2. And I might mix together the Leslie matrix equations, just because I ended up trying this out and it took me, well, too much time. So let's just leave it at that. And so I will be making it significantly shorter. But these are the types of questions that I expect you to be able to solve for quiz 2, which will be next week. So not this tutorial, but the tutorial next week. There were a couple of questions in chat, so let me try to go through them all. So I think the first one was about what the, yes, so the quiz is not going to cover this week's material on multivariable calculus. So it's only going to cover the linear algebra from last week. Let's see, there is only a final exam in the class. The class, as I mentioned at the beginning of class, the marking scheme is 5 quizzes, participation mark, and the final exam. Yep. Yes, quizzes are 40 minutes now instead of 30 minutes. So that vote did pass. I'll send out another. Oh, I forgot to send out the email with the updated syllabus. But basically, the quizzes are 40 minutes by default instead of 30 minutes. And though I am trying, yeah. So that is confirmed. Okay. Does anyone have any other questions before we get started with this week's material? Okay. If not, let's go ahead and get started. So we're going to be talking about functions of several variables. In order to do that, we first need to ask ourselves, well, what's a function? You guys have seen this before. What is a function? So I'm going to do this in a slightly more mathy and slightly more abstract way. So a function takes an input in some set of things v and gives a single output in some set of things w. So now the easiest example is when v and w are both the real numbers. And so this is what you guys are probably most familiar with, since this is the subject of most of your early math classes at least. So let's give a simple example. F is from the real numbers to the real numbers, where let's say f of x is equal to x squared. So then f of 5 is equal to 25, f of minus 1 is equal to 1, etc. Okay, so that shouldn't be too surprising. You guys have been working with functions for a while now. Another classic example is where these are both the complex numbers. And so, formally speaking, a real valued function can't give you a complex value as an answer. But now if you, or take in complex numbers. But of course, there is a natural generalization where of those exact same functions using polynomials that gives you complex functions. So f from c to c. And often we write this in the same way, except the difference is you're just taking it from a different domain to a different range. So then here f of minus 1 is still 1, but f of I is equal to I squared, which is equal to minus 1, etc. Okay, we also have less mathematical examples. So like they're still perfectly valid functions, but they aren't written out quite as formally. Oh, what is a complex number? That is a good question. So complex numbers are, a complex number is something like I, which is equal to the square root of minus 1. Oh, that is a good point. I did not realize that you guys haven't learned complex numbers yet. That will be a topic of a future lecture, Len. So I will make sure to cover that again. That's not so important in this particular. So basically, you guys, let me give a quick explanation before moving on. So basically, when you take a square root, you can't take the square root of negative numbers, right? So what happens if you define the square root of I to be equal to minus 1? This allows, and then you have numbers that are of the shape a plus bi, where a and b are real. So if you do lat, then you get list set is equal to the complex numbers, where you have something plus something else times the square root of -1. Now, the square root of -1 isn't the real number. It's some other magical thing that we define as the imaginary unit I. So these are complex numbers. We'll have to go into a little bit more detail about that later. I mentioned them in the last lecture because when you have eigenvalues that are complex numbers, you end up having these weird rotation operations. And so these do play a very important role in, well, in physics as well, because you often have imaginary parts of state vectors. But that is not so important for mathematical biology for the most part, so let's skip that for now. I will come back to it later when it becomes important. Okay, but we also have some less mathematical examples. For example, you might have the set of days, and B might be the set of days, and someone asked, complex numbers are an imaginary number multiplied by a real one. Yeah, so complex numbers are imaginary numbers multiplied by real ones, and possibly if you then add some other real numbers. So that's a good way of thinking about complex numbers. So you can take an imaginary number, multiply it by a real one, add it to a real number, add it to another complex number. You can do all the same things you do with real numbers, except it's just a bigger set of things you can do since now you have the square root of -1. But yeah, so let's give this last mathematical example though. So suppose we have a set of days and we have a set of emotions. So for example, maybe you're happy today. So f of 2021 June 9th equals happy for a particular person. And maybe f of 2021 June 16th, maybe you guys will be anxious next week because we have an upcoming quiz next week. But these are still functions. They map a particular something from one set into something from another set. So let's try that out. Sorry, something went wrong with my PowerPoint. So let's start with this one. So try this out. Is this a function? You have a set of people mapping to a set of colors, where given a particular person, f tells you what their favorite color is, assuming each person has exactly one favorite color. Okay, looks like we're getting a lot of yeses. Yes, this is a function because for each person it tells you exactly one color. What about this other function? So let's say we have a set of persons mapping to a set of colors. Where given the person, G tells you all the colors they like. Oh, actually, let me reset this before. Yeah. Tells you all the different colors they like. Okay, yep. So we're getting, looks like a lot of B's in chat. Yes, exactly. This is not a function because it maps one thing to many things. Now, it's slightly more complicated than this, because what happens if we have the set H, which maps from set of people to all the sets of colors. For given the person, H tells you all the colors they like, and this can be multiple things. Yeah, so this is a function again because you can have multiple colors in a single set, and so even this is still a function. It's just mapping from a different set to a different to the set of all sets of colors, and so this is actually a function. Let's go ahead and give a couple more. So let's say we have photos on Reddit where that map to a value between that's either 0 or 1, which returns a 1 if the photo has a cat, and returns a 0 if the photo does not have a cat. So is this a function? So we're starting from a set, which is the set of photos on Reddit, and we're returning a set, which is the set of 0 and 1. Okay, so it looks like everyone answered A. Yes, this is actually a function. It's a little bit weirder of a function, but if you have been keeping up with the news, these are the sorts of functions that are learned by artificial intelligence when they're trying to figure out whether a photo has a cat in it. This is the mathematical formalization of that idea. So we have a question in chat. Is a function also technically a program? That depends on how you define program as well. So a program does something, right? programs can have side effects, which is one of the differences between programs and just pure functions. So, like, a program can knock over, if you program a robot, you can program it to knock over a glass of water. That is no longer a function because it's not just the robot telling you something, it's the robot's doing something. And so, depending on how exactly you define function and how you define program, they're not quite the same thing, though they are related. So, they both take in an input. So you give it some input, and then they give some output. But programs can have side effects, which is one of the other differences, which we're not going to cover too much in depth here, since this is not a computer science class. But like, if you're in a computer science class, that will be one of the distinctions between different types of programs. And when the quadratic equation is not a function, right? Yeah. So the quadratic equation isn't a function by this definition because it outputs two different answers. So you could think of it as a function to the set of numbers. The Reddit example would be a type of program. Yes, so you can certainly program a function. You can write a program to return the output of a function. And yes, exactly. So someone has written a program to go on Reddit and classify if the picture has a cat or not. Okay, let's try one more. Or sorry, no, a couple more. So let's go back to Mathland. Let me reset. So someone had a question about the quadratic equation. Well, this probably, so you were ahead of me there. So in this particular case, I'm taking the square root, but I'm taking both the plus or minus of the square root. And in this case, exactly, this is no longer a function because you get multiple answers for a single initial answer. Which is why often when we talk about these things as functions, what we do instead is we talk about just the positive square root. So this one here, this one is actually a function because by convention we refer to the square root of x as just referring to the positive square root unless we specify otherwise. And it looks like everyone basically agreed. Nice. Okay, one last one. What about this one? So this one's a little bit more complicated. So I have some function, something h, that takes something from a 2D plane to the 2D plane by this matrix multiplication. Is this a function? Yep, so this is actually indeed a function. Oh, so there was a question in chat. Cube root. Yes, cube root is generally a function. Because you get a single answer out of it, basically. Okay, so this is also a function, and this is a function that's in a slightly different space. So you're starting from the space of points on the plane and mapping to the set of points on the plane. And these are all functions. And this is what we're going to be talking about today. So functions from things that aren't just the real number line, but things that are maybe the 2D plane or the 3D plane to something else. So let's give an example of that. Let me go on to my next slide. So we're going to be talking mostly about functions that go from, say, the 2D plane to a real number. So this is one of the easiest types of multivariable functions. So given a vector x, y, so a point in the plane, the output is a real number. Let's see, we have a question. Can you go from 2D to 3D, or would that not be a function? You can absolutely go from 2D to 3D. You can in fact go from any dimension to any dimension, and you can still have a function, depending on what you write down, of course. So in this case, this is one of the most common types of multivariable functions. So instead of writing in this vector way, we often write it just f of x and y for convenience. So f can be thought of as a function of two real variables. And let's give a couple examples of this. Let's see, example, f of, let's say, xy is equal to, let's say, this function is 2, 1, the row vector 2, 1 times the column vector of whatever you put in, so that's equal to 2x plus y. And then if you plug in the number, so f of 1, 5 would be equal to 2, 1, 1, 5 is equal to 7. Since we had a question about this 2D to 3D, maybe I'll make that one of my examples. I will have examples like that later. But basically, when you're going from 2D to 3D, you should think of it not as 3 different real numbers, but you should think of that as a point in a 3D space. So instead of thinking about each of the numbers as a single object, you're thinking about the point in the 3D space, and that's the set that you're going to. And so that's why you're not going from 2 answers to 3. So this is why I had that example of the set of colors, where a set of colors here, the set of all sets of colors. Because that can still be a function, this function h here from set of persons is a set of all sets of colors, even though you have multiple answers. Because what you're doing is you're saying that your answer is in the space of the set of multiple answers. Does that make sense, Sam? Okay, but let's give a couple more examples of this basic type of multivariable function first, since we're going to be using this one a lot. So this basic type of multivariable function, you're starting with two different things, and you're ending up with a single number. So let's say this particular function, f of xy is equal to, let's say this is xy, xy. So the dot product of itself, so this is x squared plus y squared. So f of 1, 5. So we can also write it this way, is equal to 1 plus 25 is equal to 26. Yeah, exactly. So we have in chat, it can be, so functions are from one set to another set. And so long as you say which sets they are, the sets can have different numbers of, they can have different amounts of numbers in them if they're vectors of different dimensions. And that can still be a function. You just have to be careful what you're defining. So if you say that your function is from the real numbers to the real numbers and you have two answers, then it's not a function. But if you say it's from the real numbers to the 2D plane, then it is a function. Okay, let me give one more. So let's say g of xy is equal to x squared e to the y plus 5xy. So you don't have to define them in the sort of vector way. You can just directly define it based on the variables. Then g of 1, 5 is equal to e to the 5 plus 25. Okay, so each time you're just plugging in these numbers for x and y whenever you have multiple real numbers. Now, these things are ubiquitous all throughout mathematical biology and, well, I mean, modeling in general, because often you have more than one variable. So let's give a quick example of a body mass index. So this was developed to approximately quantify obesity. So B of mh is equal to m divided by h squared, where m is mass and in kilograms and h is height in meters. And this is a quick way of figuring out, it's a proxy for whether or not a population is overweight or obese. Now, you have to be a little careful when you apply this to any individual because this is just an approximation, but it is very helpful, and you may have seen news articles about the obesity rate, and often that's using something like the body mass index as a definition. And so this is a function of two variables. So for example, if you happen to have, say, a male who is 68 kilograms at a height of 1.71 meters, let me reset before you guys answer that poll, because otherwise, yeah. Okay, you guys can answer that poll while you're thinking. So if we have this, then what you're doing is you're plugging in these two values. So B of mass and height is equal to 68 kilograms divided by 1.71 meters squared. So that will be equal to 23.3 kilograms per meter squared. So this is normal weight by this definition. So this is a very imperfect proxy, but it is one of these functions that you may use. So let's see. Now, when was this invented? What are our replies? Okay, so we have some replies some replies for 1700 to 1800, a bunch from 1800 to 1900, a few from 1900 to 2000. Okay, so you guys are correct. BMI was invented in sometime between 1830 and 1850 is roughly when the guy, Adolf Quetelet, I can't pronounce the name, I'm afraid. But yeah, so that's when that was invented. So it was in the 1800s. Okay, so basically what we're just showing is that often you have more than one variable you care about and you want to output some value. So now let's talk about this a little bit more generally. So a function of several variables, and so you can is from Rn to n, is a function from n real numbers that outputs one real number. And there are a bunch of, you don't have to stop at just two variables, but here this function's from n to, so a common example is, let's say, the volume of a rectangular prism. Let's say a right rectangular prism. So the volume of a right rectangular prism, so that looks something like this. So where you have a height, you have a width, and you have a length. And so then the volume of the height, width, and length is just equal to multiplying all these together. So if h is equal to 1 centimeter, w is equal to 1.5 centimeters, and L is equal to 4 centimeters, then the volume of this rectangular right rectangular prism is equal to 6 cubic centimeters. And you can write these things more generally, so you can have f of, note that f of x, y, z is equal to 0 is a multivariable constant function. So for any inputs, you output the same thing, but it is still a function because you output only one thing. Okay, so now we've talked a little bit about these things in general. Let's think about what these things mean as geometrically. Come on. So what's the geometric interpretation of these things? So if you have a function from R to R, it maps a real number to a real number. So we can think of each function as pairs of numbers in R cross R. So these are ordered pairs, right? So you have two real numbers, which is what we do when we draw the graph of a function. So let's remind you all of this. So if you had a function f of x is equal to x squared, well, you might have a bunch of points. F of 1 is equal to 1, f of 2 is equal to 4, f of 3 is equal to 9, etc. So you can think of this as a map from 1 to 1, or from 2 to 4, or from 3 to 9. And if you have these maps, well, you can think of this as, let me use green, an ordered pair, 1, 1, 2, 4, 3, 9, etc. And this here is the, you can graph this out, so there's the x-coordinate, and there's the y-coordinate, which is equal to f of x is equal to x squared. And when you graph this out, what you end up with is something that looks like a parabola. So this is what we mean when we say the graph of a function. That is not the best parabola, but it'll hopefully do. So now, how do you interpret a two-variable function? Well, you can think of it as taking any point in the plane. Come on. Yeah, you can think of it as taking any point in the plane, so any ordered pair there, and then drawing a surface in R3. So you start on the xy plane, and you map something up to a point in on the z-axis. So let's give an example of this, and then we'll show it in some plotting software as well, since that'll make it a little bit more obvious. So let's give a simple example. Let's say f of x and y is equal to x plus y. So this is a very simple multivariable function. Then you have f of 0, 1 is equal to 1, f of 0, 2 is equal to 2, f of 1, 1 is equal to 2, f of 2, 1 is equal to 3, and so on. And of course, you can do the same thing. So the point 0, 1 maps to 1, the point 0, 2 maps to 2, the point 1, 1 maps to 2, and the point 2, 1 maps to 3. And of course, we can write this as an ordered pair. I think I used green a moment ago. 0, 1, 1, 0, 2, 2, 2, that's a 1, 1. Oh, sorry. 1, 1, 2, and 2, 1, 3. Okay, so if we're given that, then if we draw this out, so I'm only going to draw a single point because drawing 3D is hard, and I'm going to have a computer do it for me. Let's have this be our x-axis, that be our y-axis, and this be our z-axis. So let's say this is 1, 2, 3, 4, 1, 2, 3, 4, and let's say we had this is 1, 2, 3, 4. And 1, 2, 3, 4. So when you're drawing this out, the first thing you do is let's draw out a particular point. Let's draw out this 2, 1, 3 point. So on the x-axis, you go forward 2, and then you go down to this point. So this point here is the point 2, 1 on the xy plane, and you have to go up 3. So if we go up 3, then what we're going to get is 1, 2, 3. So you're going to go up to that point, and let me draw out a square up there just to make it a little bit more obvious. So lat is going to be our point 2, 1, 3. Okay, so basically you're specifying a coordinate in 3D space, and you can do this for every one of the points for every point in xy, and so you end up getting a surface on xy. What does this look like? Well, we can show it by plotting this in 3D. So let me switch over to my Chrome capture, and wait, where was that? There. So if you plug this into GeoGebra or any other surface plotting thing, you'll see that this is a plane in 3D space. Okay. And let's see. We can also give a couple more examples of these sorts of surfaces. So here I have a more complex surface. Over here on the left, I wrote down the actual equation. On the right yeah, so I'll switch back to the plot again. And I'll give you a little bit of time to play with these later. So if you look over here, I also gave you what you need to type into GeoGebra in order to get these things. Oh, actually, let me copy and paste some of these. So let me put this in chat. So if you go there, you can type in things on your own and play with different shapes. So this is geogebra.org. And so you can play with all sorts of different shapes. And so basically what you see is that for every point on the XY axis, let me actually show this one as well. For every point on the 3D axis, you end up getting a point in the Z going up or down. And so this defines some surface. And if you want, you can move the surface around. So for example, if I add 1 to it, the entire surface moves up. And so then you can still see sort of what's going on. You've just shifted the entire thing. Or if you want to, say, add another, let's say, if you want to subtract out e to the x, then this is going to give a very different surface because then it starts decaying really rapidly and falls off. And so these are the shapes these multivariable functions give you as a surface in this 3D space. I think I have one more example. So let me switch back to my PowerPoint. So this is another complicated example. If we switch back to Chrome, you can see this sort of shape. So you can see all sorts of complicated shapes, and these are the surfaces that come out from these multivariable functions. So if you go from, and one of the nice things about going from a two variable function to a one variable function is that you can plot these things out in 3D because they end up as points in the sort of 3 space. Unfortunately, you can't do this if you have an n variable function because it's hard to plot in n+1 dimensions. But this is useful in getting some intuition for what's actually going on. You'll see that you have two different xy axes on the horizontal plane, and then what these things do is they assign a particular point in the z plane for every point in the xy plane. And I think this is a good point for, are we expected to know how the plot looks for a certain function looks like? No, not in general. I'm just trying to give you intuition for what's going on here. So I will actually never expect you to plot one of these by hand. I have never plotted an entire one of these by hand. This is what calculators are for. But it gives you some intuition for what's going on. Yes, it would be such a mess. Like, you saw how hard it was for me to draw just a single point. Just imagine how hard it would be for me to draw this entire surface. But these surfaces, these visualizations, do give you a sense of what's going on with the functions, and sometimes it's useful to visualize them. In fact, if you go back to, and there are different ways of visualizing them. So this is just one way of visualizing. Another common way of visualizing, let me go back to my PowerPoint, is in these sorts of more surface plots, right? So another way you can visualize these is you can just have different colored bands corresponding to the different values of your function. So that's a little bit more typical of a way to visualize these things, depending on what exactly you care about. But yeah, so these are 2D to 1D functions, so from R2 to R. And There are, of course, other types of functions, so like from R2 to R2, or from R2 to R3, etc. So you can have all sorts of functions, but this is just the simplest example of a multivariable function, and we'll be talking about things like derivatives of these more complicated functions and integration with them in the, well, later half of this lecture. So this, I think, is a good moment for me to give you all, let's say, a 6-minute break, so the 12:47, and I suggest you guys try it out yourself. And so I've given you the functions as well as what you need to type in GeoGebra in order to get these functions to show up. So have a go at it, and I will give you a brief break to have a go at it, and then switch over to the next segment of the lecture, which will be partial derivatives.